Section 250.96b of the National Electrical Code, or NEC, addresses ensuring electrical continuity of the grounding path between metal raceways and boxes. It outlines several acceptable methods: firstly, metal-to-metal contact between threaded hubs and enclosures; secondly, clamping or set screw type fittings; thirdly, bonding jumpers; and fourthly, other approved means. Section 250.97 emphasizes the need for suitable bonding jumpers or other approved methods to guarantee electrical continuity between all raceways, cable armor, and other metal enclosures. EMT connectors are generally recognized as an approved means for grounding, specifically mentioned in Section 250.104 of the NEC. This implies that under normal circumstances, the use of an EMT connector on a 3/4-inch EMT power feed entering a disconnect for a crane, even with concentric and eccentric knockouts, can be considered sufficient for providing a bond. However, there can be exceptions that necessitate additional bonding measures. The inspector might have been referring to Section 250.102b of the NEC. This section pertains to bonding jumpers around EMT bodies. It states that bonding jumpers around EMT bodies shall be used only where necessary to assure electrical continuity. This does not completely prohibit the use of bonding jumpers around EMT bodies. It clarifies that they should be implemented when they are required to establish and maintain electrical continuity. The core principle here is to ensure a reliable low-impedance ground fault current path. When dealing with concentric or eccentric knockouts in enclosures, the integrity of the electrical connection can be compromised. These types of knockouts introduce discontinuities in the metal enclosure, potentially increasing impedance and hindering the flow of fault current. In such situations, a grounding bushing can provide a supplementary bonding path, bypassing any potential impedance issues created by the knockouts. Therefore, even though EMT connectors are typically approved for grounding, the specific circumstances of the installation, particularly the presence of concentric or eccentric knockouts, may necessitate a grounding bushing to meet the requirements of the NEC and ensure electrical safety. The grounding bushing supplements the connection made by the EMT connector, providing a more robust and reliable grounding path, especially important for equipment like cranes where safety is paramount. Essentially, the code prioritizes maintaining a continuous and effective ground fault current path. While an EMT connector might be adequate in some scenarios, the presence of knockouts introduces a variable that demands further consideration and potentially a supplemental grounding method to comply with code and best practices. Think of the grounding bushing as a safety net, ensuring that even if the primary grounding path is compromised by the knockouts, a reliable alternative exists. This is why inspectors may require grounding bushings in situations involving knockouts, even when EMT connectors are used. The ultimate goal is to provide a safe and effective electrical system. The NEC provides a framework, but the inspector's judgment is crucial in interpreting and applying the code to specific field conditions. Always prioritize safety and consult with a qualified electrical professional if there are any doubts about the proper grounding and bonding methods. It is also worth noting that the size and type of grounding conductors and bonding jumpers are critical. These must be selected based on the size of the overcurrent protective device in the circuit, as specified in NEC Table 250.102. Using undersized conductors or jumpers can compromise the effectiveness of the grounding system and create a safety hazard. Grounding and bonding are not merely about complying with the code. They are about protecting people and property from electrical hazards. A properly installed and maintained grounding system provides a low impedance path for fault current to return to the source, allowing the overcurrent protective device to quickly clear the fault and prevent electrical shock or fire. Therefore, it is imperative to take grounding and bonding seriously and to follow all applicable codes and standards. Now let's dive into a more detailed explanation of what electrical continuity means in this context. Electrical continuity refers to the presence of an uninterrupted path for electrical current to flow. In grounding systems, this means a continuous, low impedance path from metal enclosures and equipment back to the source of power. This path allows fault currents to flow quickly and safely, tripping circuit breakers or blowing fuses to energize the circuit and prevent electrical shock or fire hazards. The NEC mandates that this electrical continuity be maintained throughout the entire grounding system from the service entrance to the furthest point of utilization. Any break or high impedance connection in this path can impede the flow of fault current, potentially delaying the operation of overcurrent protective devices and increasing the risk of electrical hazards. This is why the code emphasizes the use of approved methods and devices for grounding and bonding, such as those listed in section 250.96b, to ensure reliable electrical continuity. One common cause of discontinuity in grounding systems is corrosion. Over time, metal connections can corrode, increasing resistance and reducing the effectiveness of the grounding path. This is especially a concern in damp or corrosive environments. To prevent corrosion, it is important to use corrosion-resistant materials and to protect connections from moisture and chemicals. Another potential source of discontinuity is loose connections. Vibration, temperature changes, and physical stress can cause connections to loosen over time, increasing resistance and compromising electrical continuity. Regular inspection and maintenance are essential to identify and tighten any loose connections. Improper installation practices can also lead to discontinuities in the grounding system. For example, over-tightening connections can damage conductors or fittings, while under-tightening can result in loose connections. It is important to follow manufacturer's instructions and to use appropriate tools and techniques when installing grounding and bonding equipment. The NEC also addresses the issue of induced currents in metal raceways and enclosures. When conductors carrying alternating current are run through metal raceways, they can induce currents in the raceway itself. These induced currents can create circulating currents and voltage drops, potentially interfering with the operation of sensitive electronic equipment or creating a shock hazard. To minimize induced currents, the NEC requires that metal raceways be bonded together at frequent intervals. This provides a low impedance path for the induced currents to flow, reducing circulating currents and voltage drops. In addition to bonding, the NEC also allows for the use of non-metallic raceways in certain applications. Non-metallic raceways do not conduct electricity, so they cannot induce currents. However, it is important to note that non-metallic raceways must still be properly grounded to provide a path for static electricity to discharge. Static electricity can build up on non-metallic surfaces, especially in dry environments. If this static electricity is not properly grounded, it can discharge suddenly, creating a shock hazard or damaging sensitive electronic equipment. Therefore, it is essential to follow all applicable codes and standards when installing and maintaining grounding systems, regardless of the type of raceway used. Now let's move on to a discussion about impedance. In alternating current circuits, impedance is the total opposition to current flow. It includes resistance, which is the opposition to current flow due to the material of the conductor, and reactance, which is the opposition to current flow due to inductance and capacitance. A low impedance grounding path is crucial for effective fault current protection. The lower the impedance of the grounding path, the more fault current will flow, and the faster the overcurrent protective device will operate. High impedance grounding systems, on the other hand, limit the amount of fault current that can flow, potentially delaying the operation of overcurrent protective devices and increasing the risk of electrical hazards. There are several factors that can contribute to high impedance in a grounding system, including long conductor lengths, small conductor sizes, loose connections, and corrosion. To minimize impedance, it is important to use short, direct conductor runs, appropriately sized conductors, tight connections, and corrosion-resistant materials. The NEC provides guidance on selecting appropriate conductor sizes and materials for grounding systems. Table 250.102 code specifies the minimum size of grounding electrode conductors based on the size of the service entrance conductors. Table 250.122 specifies the minimum size of equipment grounding conductors based on the size of the overcurrent protective device. In addition to conductor size, the NEC also addresses the issue of conductor material. Copper is the most common material used for grounding conductors because it is a good conductor of electricity and is relatively corrosion resistant. However, aluminum conductors are also permitted in certain applications, provided that they are properly sized and installed. When using aluminum conductors, it is important to use connectors and fittings that are specifically designed for use with aluminum. Aluminum is a softer metal than copper, and it can corrode when in contact with dissimilar metals. Therefore, it is essential to use appropriate connectors and fittings to prevent corrosion and ensure a reliable electrical connection. Let's talk more about bonding jumpers, which are conductors used to connect different parts of the grounding system together. Bonding jumpers are used to ensure electrical continuity between metal enclosures, raceways, and equipment. They provide a low impedance path for fault current to flow, helping to protect people and property from electrical hazards. The NEC requires that bonding jumpers be sized according to Table 250.102 Current, which specifies the minimum size of bonding jumpers based on the size of the overcurrent protective device. Bonding jumpers must be securely attached to the metal enclosures, raceways, and equipment that they are connecting. The connections must be made using approved methods such as welding, brazing, or the use of listed connectors. It is important to ensure that the connections are clean and free of corrosion. Corrosion can increase the resistance of the connection, reducing its effectiveness and potentially creating a safety hazard. In some cases, it may be necessary to use more than one bonding jumper to ensure adequate electrical continuity. This is especially true in situations where the metal enclosures or raceways are large or have multiple sections. The NEC also addresses the issue of bonding dissimilar metals. When connecting dissimilar metals, such as copper and aluminum, it is important to use connectors and fittings that are specifically designed for use with dissimilar metals. Dissimilar metals can corrode when in contact with each other, increasing the resistance of the connection and potentially creating a safety hazard. There are several different types of connectors and fittings available for bonding dissimilar metals. These connectors and fittings are designed to prevent corrosion and ensure a reliable electrical connection. Ultimately, compliance with the NEC is not just a matter of following rules and regulations. It is a matter of ensuring the safety of people and property. By understanding the principles of grounding and bonding and by following the requirements of the NEC, electrical professionals can help to prevent electrical shocks, fires, and other electrical hazards. Remember, safety should always be the top priority.